Hi guys, we're looking at text and test 4, page 471, exercise 7, 12.5, sorry. Um, all of these are inequality proofs to show that one thing is greater than another or greater than or equal to. And a lot of them are based around this idea that any number squared will be positive. That's a positive number. It's 9. Minus 5 by minus 5 is 25. Even if there's a decimal or fraction in there, minus 5.2 by minus 5.2, you get a positive answer because it's negative times a negative. So we get a squared generally is positive, b squared is positive, and this comes up quite a lot as well. A plus b squared is going to be positive. A minus b squared is going to be positive, okay, because even if that comes out as a negative number, you're squaring it, it's still going to be positive. If you put a minus sign in front of a positive number, you get a negative number. Same thing, a minus b squared with a minus in front of it. That's a negative, okay? So if you want a number that you can say is always positive, if you can write it in that, it's called completed square form, or here, you can say it's positive. If it's completed square with a minus outside, then it's always a negative number. You can always say that. So question 2 is one like that. It says, show that a plus b squared is always greater than 4ab. And one way to do this is to find an equivalent inequality. So if I multiply this out, square the first, square the second, twice the product is what I get on the left-hand side, is greater than 4ab. But if I move that 4ab over, I get a squared plus b squared minus 2ab. It's greater than 0. Okay, that's moving that over, changing it to a minus 4ab. So if I can write that as a completed square, then I can say it's always a positive number. Well, look here, I've got square the first, square the second, and twice the product. It's just that it's not a plus b anymore. That's a and b. Square the first, yes. Square the second, yes. To make that twice the product, I need a minus in there. Okay, so that's equivalent, and that's greater than 0. Well, that's it proved. Okay, so this I know to be true. So this equivalent statement up here must also be true. Okay, so that's it proved. You can say therefore a plus b, a plus b squared is greater than 4ab. Question 4 says a plus 1 over a is greater than or equal to 2. If a is positive and b is positive, show that. So it actually does say, for part 1, we just know that a is a positive number. Okay. Well, multiplying through by a gets us something that looks like a quadratic. And that's what we want to, that's a 1. That's what we want to show. If I move this over, a squared minus 2a plus 1 is greater than or equal to 0. Yeah, so if I can show an equivalent relationship here is true, well, then I know the original relationship is true. Now, this one doesn't lend itself quite, sorry, it does, yeah. A minus 1. Square the first, a squared. Square the second, 1. Twice the product, minus 2 by a by minus 1 gives minus 2. Okay, so there it is, a minus 1 squared. I can write this in completed square form, and I can say, well, therefore, it's positive. So this is a true statement. I know that because this is a square number is always greater than 0. This equivalent statement must therefore also be true. Question 5, prove that a squared minus 6a plus 9 plus b squared is greater than 0 for all real values of a and b. All of these assume that all of the numbers we're working with are real, that we've no imaginary parts or complex numbers or anything like that. Well, what have we got here? We've got a completed square part there. Okay, that's square the first, square the second, twice the product, a, and that's 3. Squared is 9. Just needs a minus sign in the middle. I made a mess there. Okay, square the first, yes. Square the second, yes. 2 times a times minus 3 gives minus 6a. So there's my completed square part plus b squared. And, well, can I say that that's greater than 0? Yes, because that bit there is positive because it's a square number. And that bit there is also positive because it's a square number. Strictly, actually, all I can say is that this is greater than or equal to 0. Sorry, yeah. So it might actually be 0 if A had a value of 3 and B had a value of 0. So you can see here the same patterns cropping up again and again. So I'm only going to do 2 more, even though there's a whole bunch of questions in this exercise. We'll do a lot of those in class. This might take 2 classes to get through, I'd say. Question 6, part 4 is x squared minus 6x plus 10. Show that that's greater than 0. Now, you don't actually have a completed square here. But if you separate it out, x squared minus 6x, well, what do you want? Remember the rule with completing squares is half of this number. So 6 over 2 squared. You want a 9. Okay, so let's just rewrite it. So it's x squared minus 6x plus 9 plus 1 instead of plus 10. Now I can say this bit here is a completed square. That's square. The first is x, and 3 is square the second. Twice the product needs a minus. So that's x minus 3 squared gives x squared plus 9 minus 6x. Plus there's one more out there. Is that greater than 0? Well, yes, it is, because the smallest value this can possibly have is 0 plus 1. Okay, so then this number has to be at least 1. So is it greater than 0? Yes, it is. Okay, and you're going to use that trick of completing the square in question 6 a lot. We'll see that in class. I'll finish up here with question 9, which says factorize a cubed plus b cubed. But that's the sum of 2 cubes. If you go back all the way to chapter 1, page 13 in this textbook, you'll see an expression for the sum of 2 cubes. You might have learnt it off or found some way to remember it, hopefully, because it comes up reasonably often, and it's a good one to have in the toolkit to have learnt that off. Here it is anyway. It's a plus b multiplied by a squared minus ab plus b squared. And what they've asked you to do, hence prove that a cubed plus b cubed is greater than a squared b plus ab squared. Okay, well, factorizing the left-hand side there gives us a plus b times a squared minus ab plus b squared. Is that greater than a squared b plus ab squared? I can factorize this as well. You have a common factor of ab multiplied by a plus b. And because you're told in question 9 that a and b are positive numbers, I should have said that at the start, a and b are positive numbers. So a plus b is a positive number, so you're allowed to divide through the inequality by a plus b. So divide both sides by a plus b, and an equivalent expression here is a squared minus ab plus b squared is greater than ab. So can we prove that? Well, let's bring the ab across. A squared minus twice ab plus b squared is greater than 0. Can we prove that? Yes, we can, because this is square the first, square the second, twice the product. That's an a and a b, a squared, b squared, twice ab. You just need a minus sign to complete that. Squaring that, that's true. Therefore, you can say this original statement up here is also true. Okay. I'd like you to give question 1 and question 3 a go now, and we'll look at the rest in class. Thanks.